We're going to look at a linear regression t-test. I think I have that at the top. Significance test for the slope. So here's the situation. Do customers who stay longer at buffets give larger tips? So a statistics student who worked at an Asian buffet decided to investigate this question. While doing her job as hostess, she obtained a random sample of receipts which gave the length and time in minutes that a party was in the restaurant and the tip amount in dollars. And here's a computer output of the data. So let's talk about what the computer output tells us. So we can see here, time down here is our explanatory variable. Next to the explanatory variable is always the slope. The constant is our y-intercept, and so this is our y-intercept. So the regression equation here could be written as the predicted tip is 4.535 plus 0.03013 times the time spent in the restaurant. Now, so this part of the spread of numbers is important. We're also going to be looking at the standard error of the coefficient, in this case the standard error of the slope, the t-statistic, and the p-value for a hypothesis test for the slope. The numbers in the line above are for a hypothesis test for the y-intercept. We also see S is the standard deviation of the residuals, and we have our r-squared value. You don't have to worry about the r-squared adjusted. We have some graphs here. There's the scatter plot of time versus tip. Here is the scatter plot of the residuals, and here is a histogram of the residuals. So thinking through the conditions, which I'm going to just say pretty quickly, we have the linear condition. It looks like the data is fairly linear. We see no obvious bend in the residuals, so we've satisfied our linear condition. The data are independent because we have a random sample of people that went to this restaurant, so we have no reason to think they're associated with each other in any way. We also know that the 12 that were sampled here are less than 10% of the population of all the people that go to this restaurant. We have the normal, the residuals follow a normal model. We have no reason to question that because there's no obvious skew or outliers in this residual plot. Equal variance of the residuals, or equal standard deviation of the residuals. So as we go from smaller x's to larger x's, we see that the amount of variability in the residuals is fairly constant. We have fewer people who only ate for 20 minutes in the restaurant or who stayed for 100 minutes. We have most of our data in the middle, so we don't have enough data to see it really well, but we don't see any obvious problems with that. And then, of course, we have a random sample, which would satisfy the random. So I am just going to show you the written out conditions here. Feel free to pause the video and write these down. Other than that, I'm going to move on. Okay. Now, we need to have some hypotheses for our hypothesis test. So we are trying to find out if a greater number of time in the restaurant results in a bigger tip. In other words, we're looking to see if there is a significant positive linear relationship. So is the slope significantly greater than 0? All right. So our null hypothesis here is that the slope equals 0. We're going to use beta to represent the population slope. So we're saying the population slope equals 0. In other words, there is no linear association between time and tip. Okay, now our alternate hypothesis is that there is a positive linear association. In other words, our slope is greater than 0. So a positive linear association between time and tip. And I'm not going to write that down, but there is a positive linear association. Now, we've done the conditions already, so the next thing we're going to look at then is what do we need to do to run the test. So these are where some important numbers come in. The numbers that we need we have our t-statistic, our p-value, and we're going to end up using the standard error of the coefficient. I want to show where these numbers show up on the linear regression t-test, but we probably ought to do that test on the calculator first. So if you haven't yet, go ahead and get your calculator out and enter those two lists of data that are at the top of the page, and then you can do this along with me. Okay, I have my data in here, and I'm not going to go ahead and make all the graphs this time. Of course, you can do a linear regression and make the graphs on your calculator, but I'm going to show just how to do the linear regression t-test. So I'm going to insert a calculator page, go to Menu, Statistics, Stat Test, and then I'm going to find the linear regression t-test, which is right here. And I'm going to enter my value, my X list, which is time, my Y list, which is tip, and my alternate hypothesis, which is that beta is greater than 0. The other symbol represents the y-intercept in case you also want to do a significance test on the y-intercept, but we don't do that usually in the statistics class for AP Stats. So here's all of our values, and these are the same ones you should see on the paper, the notes paper. So I'm going to go back to the notes paper, and we're going to just talk about these numbers now. So that's where you get these numbers from. I want to remind you too that you can make a residual plot by using this residuals here. So we have, if we go to stat resid and push enter here, we can get all the residuals. If you create a list and store this to a list, then you can make a residual plot and a residual histogram of the residuals and all those things that you need. Okay, so we see here important numbers. We have our t-statistic right here, which is the same number you see in the computer output above. You have your p-value, which is not the same number as you see in the printout above. So we're going to talk about that in a minute. We have our degree of freedom. We have the regression equation a plus bx with a. There's our y-intercept and our slope, so we have that. We still have our standard error of the residuals right here, and the standard error of the slope, which is an important number that we're going to need. So everything is the same except the p-value. So what's the deal with the p-value? Well, it turns out, I'm going to go ahead and write a little note about the p-value here. So on computer output, we are always doing a not equal to test, which means that we are looking at a p-value in both tails. Remember, that's called a two-tailed test. So we have p-value as twice as big as it would be if we're doing a one-tailed test. This is just a greater than test. So for a greater than or less than, you use half of the p-value. From the computer output. So if you're using computer output and you want to do a greater than or a less than test, you'd use half of the p-value, or just do a not equal to test with computer output. But in here I am going to do a greater than test, so I'm going to use my p-value from my calculator here. So in the do step, we're going to calculate our test statistic. Now our test statistic is always the sample statistic, in this case b, our sample slope, minus our population slope, which we call beta, all over the standard error of the slope. So standard error of b. Sometimes we put that in parentheses, sometimes use it as a subscript. So our sample slope is right here, 0.03013. Our population slope comes from the null hypothesis. This is what we are hypothesizing, that there is no association. So our sample slope, our population slope is 0 according to the null hypothesis. And then the standard error of the slope, which is found in both the computer output and on the calculator, is this number right here. And this should give us our t-statistic, which is 1.23076. This tells me how many standard deviations away my population slope is from, my sample slope is from my population slope, and then the p-value tells me how unusual that is. Well, this is only about 1.23 standard deviations from the mean, so it's not all that unusual, which is why my p-value is fairly high. It's saying there's about a 12% chance that this could happen just randomly, so that's not unusual enough for me to reject the null hypothesis. Also, you should always write down your degree of freedom when you're dealing with a t-model. So we have a degree of freedom of 10. So the conclusion here, I'm very similar to, of course, any conclusion you do for any hypothesis test. So we have a large p-value. Since p equals 0.123 is greater than alpha equals 0.05, we fail to reject the null hypothesis. We do not have convincing evidence that there is a positive linear association between time spent at the restaurant and the tip amount. So I'm going to say at the Asian buffet, since that's our specific restaurant we're looking at, and the tip amount. So if we go back and look at how to answer the question that was asked, so the question, if we go back at the beginning, up at the beginning here, got to kind of scroll up. The question is, do customers who stay longer at buffets give larger tips? We do not have statistically significant evidence of that. Okay. We have no evidence, or at least not enough, no evidence that customers who stay longer tip more. Who stay longer tip more. Okay, so there's our hypothesis test. Pretty straightforward. I guess I'm done.